Wait.
You can see it, okay.
Yeah, we can set the mood.
Alright. So tonight, I've come to tell you a little story about a man named Hippasus. But the deal is I've got a lot to cover, so that's all I'm going to say right now. Okay, customary to include that, and I got a lot to cover, so I got to get through this, so no time for that. You didn't get to learn about the author? We don't have time for that. Pythagoras. So I'm not going to get too much into Pythagoras and his life himself. I want to talk about his beliefs on the divinity of numbers. So how important was it to him? Quite a lot. Pythagoras has this ardent pursuit of truth. And, well, there was this mythological figure, Alvarez, some sage and healer. He received some kind of like future-seeing powers through slaughtering and sacrificing animals, mainly birds. Pythagoras wanted to fulfill his pursuit of truth, but not only to a degree beyond simply foresight, but also in a much less violent way, hopefully. So what he did was he made friends with the gods. He became the gods' #1 supporter. He loves them. He's like, everything that they say is right. They're so awesome. Everything, their divine dogma should not be disbelieved because they're able to accomplish all things. And the Pythagoreans then follow Pythagoras and say, Pythagoras, you're right, the gods are so good, so we believe them. So what was this magical truth that the gods revealed to Pythagoras? Numbers. So specifically whole numbers, integers. So not only are numbers found in the world, they describe the world. In fact, they make up the whole world, all the heavens. Numbers describe the world better than the natural elements do. So yes, numbers describe the earth better than the earth describes the earth. I don't quite understand that, but that's what the gods say, and that's what Pythagoras thinks, and that's fine. So here, like the Pythagoreans here, they're swearing an oath by the man I swear bequeaths to our head the Tetractis, fount containing the roots of nature ever enduring. You might be wondering, who is this Tetractis, this god fount containing the roots of nature ever enduring? It's the number 10. It's comprised of the 4 primary numbers, 1, 2, 3, and 4. You add them together, you get 10. So numbers are divine. This one number is divine, and importantly for us, measure and ratio. Pretty important to these guys. So Plato wrote this Socratic discussion between Socrates, obviously, and these 2 Athenians, Philebus and Protarchus. And Socrates is talking about how most would agree that to live an ideal life, it kind of balances the, intelligence and doing like the purity and the good stuff with stuff that's kind of, more self-centered, the stuff that you want for selfish reasons. There's like a balance of the two to get the most desirable life out of it. And so then he's talking about the classes of distinction for everything present in the universe. We've got already established our 1 and 2. The indeterminate, things with no fixed limit. So stuff like compared only in terms of each other, but not with numerical quantities. And then we've got, contrarily, the determinate, things that does have limit with definite measures. And so Socrates is talking to the guys, and he's like, I think we need a 3rd class of distinction. And Protarchus is like, oh, you're so right, Socrates, and brilliant. And Socrates is like, well, this 3rd one must be able to take the 2 and 1 and combine them in a way that is helpful. And basically, it's the determinant imposing order on the indeterminate through measure and ratio. And that's it, sorry. Through it, we're able to get stuff that makes life wonderful. And an example of this, so for instance, something that would have been classified as indeterminate is hotter versus colder because they didn't have thermometers in 500 BC. So they thought that those weren't numerical. But if you are precise enough with the numerical measurements, you're able to get climate, which has to be very precise for us to live. Same thing with health and music and whatever. And then he's like, I think we probably need a 4th method of distinction as well that allows for this 3rd one. And then Protarchus is all, well, yeah, Socrates, of course. So you're telling me we got like these 2 things that we already know about, and then there's this 3rd that's kind of a uniting of the known and the unknown in a way that makes life desirable and harmonious and commensurate. And Socrates indirectly answers him and continues his train of thought. The main takeaway is this main word, commensurate. We're uniting the known and the unknown, the indeterminate and the determinate, through commensurability. You may be wondering, well, Michael, what is commensurability? I'm glad you asked. Commensurability is a very strict mathematical definition. If we're wondering about the comparison between numbers a and b, the ratio is written as so. And we will say that a and b are commensurable if a and b the ratio is a rational number. And if you're wondering what a rational number is, that basically is equivalent to the ratio of two integers. So it might be written another way, but you must be able to describe it in the form of just a ratio of two integers. And I don't know how far down we need to go with the definitions. Those are there just in case. But the main ones I want to focus on are these. So we will say that two things are commensurable if we can relate them to each other using whole numbers. So that's how we get desirable life. And the gods have not said anything about incommensurability. And basically, it's not even a thing. And since they didn't say it was a thing, the Pythagoreans are like, well, if the gods didn't say it's a thing, then it must not be a thing. Spoiler alert, it is a thing. So we enter this fine young man. Well, not young, he ended his life at like 80 years old. That's pretty good. And this guy, Hippasus, very little is like written directly about him. In fact, in Diogenes Laertius's, I don't know if I got the name right, his Lives on the Eminent Philosophers usually tries to write at least a couple hundred words on each guy. This is all he's got for Hippasus, very little. In fact, the only thing I could find that was less than that was freaking Sebes of Thebes, where the most interesting thing, the most interesting thing about that is his name. But I digress. So Hippasus, from Metaponton, he was a Pythagorean pupil and disciple. And more importantly, he was kind of different from the other Pythagoreans in the sense that he wasn't just like as traditionalist as they are. He wanted to do experiments and make discoveries. And here are a couple of things he was messing around with, most notably a dodecahedron inside a sphere. And that is a representation of that. Dodecahedron is made out of pentagons. That's going to be important later. And as I said earlier, eventually incommensurability. Main takeaway is that he is an innovator. Now, there is a bit of a division among the Pythagoreans where it breaks up into two classes, the acousmatiki and the mathematiki. The acousmatiki are those who listen. And so you remember the guys who were like, the gods, we're swearing an oath that the gods are right because they're right and we believe them just like that out of tradition. That's the acousmatiki. Very traditionalist and very much don't want to veer towards anything outside of that. Versus the mathematiki, which are more concerned with actually what makes it happen and trying to find out the roots. And I'm just going to do a quick poll here, by raise of hands. What do you think Pythagoras fits more in? The acousmatiki, raise your hands. Mathematiki, raise your hands. Okay. I understand why someone would think acousmatiki because he believes that the gods are telling the truth, so he believes them. But also remember, he has this like really deep yearning to find truth. And through his meditations, he eventually believes he's found it. The Pythagoreans, the acousmatiki, they're bandwagoners, right? They're just jumping on. They're saying, Pythagoras, we believe you, so we believe the gods, and that's all. And drama ensues when you learn that the mathematiki don't consider the acousmatiki to be true Pythagoreans. And in fact, other mathematiki say, we don't follow Pythagoras, we follow Hippasus. So a bit of tension is built. Anyway, as I alluded to earlier, incommensurability is a thing. So if A and B are incommensurable, then their ratio is an irrational number. Most famously, pi is irrational, E is most square roots and logarithms. And as also said, the acousmatiki are like, what are you talking about? The gods have not said this is a thing. You're stupid. But it only took a couple decades before it started being common knowledge that incommensurability is a thing. Like here, Aristotle is like, yeah, you're an idiot if you don't think that a square's diagonal and side length are commensurate. I have to thank for Mr. Kurt von Fritz. He's a German philologist who wrote something in 1945. I was advised not to make further jokes on the subject. Basically, he documented Hippasus's proof on incommensurability, and because it's documented, I get to show it to you today. So we get to do some mathematics. How fun. So the funny thing about it is that the proof that he ends up doing is quite intuitive. It makes sense. It uses stuff that Hippasus was focusing on, and just other common knowledge at the time. However, despite the fact that it's intuitive, it is daunting, and Mr. Fritz makes you feel like you're stupid if you don't understand it at first, but it is it is simple once you know the basis, and after you've done an hour to read through this and done through the proof yourself, and spend another hour making the proof in a way that is visible, and another 30 minutes to make sure that the proof wasn't wrong, eventually, yeah, it is really easy. So we're going to go through that right now. So we need to first build up a little bit of foundational knowledge. We need to know, and while I'm bringing this up, can I have you just pass these out? So we got to learn about isosceles triangles, pentagon and its intersections, and the method of Euclidean subtraction. So we'll start with the tricky one, which is method of Euclidean subtraction. So this is a method of finding the greatest common factor of two numbers, where basically we're trying to find the largest value where you can divide either A or B by it, or both A or B by it, and get an integer. And the way that you perform Euclidean subtraction is you start with your two numbers, subtract them from each other, get a new number, and you're going to take the two smallest numbers and perform the same thing. So you're going to subtract them from each other, and you keep going until you end. So we're all going to go through that right now. We're doing, the example on your page is 15 to 21. And so this...
By the way, these are the sheets from Heads Up.
Oh,
I'm aware. You said, is anybody going to be using these? Anybody attached to them? I was. So we're going to look at 15.
It's kind of like the infinite
Math time.
possible.
Shush, math time. 15 to 21 is our ratio that we're focusing on. So we're going to take 21, subtract 15 from it, we get 6. Take the two smallest values. 15 minus 6 gives us 9. Take the two smallest values. 9 minus 6 gives us 3. 6 minus 3 gives us 3. And eventually we get something minus something equals 0. And that something is our greatest common factor. So if you do 15 over 3, you'll get 5, an integer. If you do 21 over 3, you'll get 7, also an integer. And if your ratio is already simplified, well, if you can do the same method, and eventually you'll get 1 minus 1 equals 0, because again, 3 over 1 is an integer, 8 over 1 is an integer. But Mikey, I hear you ask, what happens if my ratio doesn't use only integers? Well, it still works actually, under certain circumstances. So I have 6/7 and 2 as an example. If you do the same process, you eventually get 2/7. 6/7 over 2/7 gives you 3, an integer. 2 over 2/7 gives you 7, also an integer. And what the heck, it even works with square roots, because you get 1 and 2, respectively. So now you're wondering, what the heck doesn't it work on? Well, it doesn't work on, say, pi to e. If you try to, I dare you to subtract pi from e and try and get anything you can wrap your head around. So what are the requirements for Euclidean subtraction to work for us to get our greatest common factor? Well, I'm glad you asked. It's our dictionary word of the day. Everybody say it with me now. A and B must be commensurate, not incommensurable, commensurable. This is important. It must be commensurable for this to work, okay? Very important. Now let's do something nicer, okay? Isosceles triangles. We all remember them, right? Two sides are the same, two angles are the same. I'm not going to do most of the when I do the proof, there's a lot of angle summations and algebra you can do to mathematically prove what you're looking at is truly an isosceles triangle. I'm not going to do it because it's boring nerd stuff. But what I am going to do is I'm going to say this is an isosceles triangle, and you're going to have to either trust me or be mad. Either one is fine, but that's what I'm going to do. And then we've got, that's a regular pentagon. There's a building that looks kind of like it. I forgot what it's called. If we take the pentagon here, we can trace two corners next to each other. We get their side length. And then we can also go through the pentagon, and get the diagonal. And if we draw the diagonal on it, you can see that we get the diagonal. And there are 5 diagonals on the pentagon. You draw them all, you get a pentagram. And if you look really closely, you can actually see there's another am I allowed to draw on this projector? Okay, well that's fine, I already did it. Look at that! There's a little pentagon right there. And the cool thing about it is now that we have another pentagon, we can get these diagonals as well. So it's recursive. You can get a pentagon on the outside, pentagon on the inside, blah, 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 blah. And it keeps going in. Very cool. Okay. So are we ready to see Hippasus' proof of incommensurability?
Yes.
Yeah! Oh, sorry, no, the D is for diagonal, S is for side length. I think it's time.
So tight.
So, We start, this right here is an isosceles triangle, trust me. This right here is an isosceles triangle, trust me. The line of importance is this line here, okay? So we can represent that with a red and a blue. So if I have a red and a blue, and I'm like, what happens if I get rid of the red? Well, I'm left with a blue. So that the way to write that is red and blue minus red equals blue, obviously. And if we look at what those colors represent, we can get the big diagonal minus the big side length gives us the small diagonal. A little trickier is the one on the right, which, thank you, we have isosceles triangle here, isosceles triangle here. I actually, in going back through this, I don't think this line was necessary in the proof, but Mr. Fritz writes it, so I'm putting it there. But anyway, that's an isosceles triangle, isosceles triangle, and then green. So now the most important line is this one, and that can be represented by either a red or a blue and a green. And that means that red equals blue plus green, or red minus blue equals green, or big S minus small d equals small s. And because of the recursive nature of the pentagons, where there's a pentagon here and you can draw further pentagons inside, both of these equations will stay true the further down you go. So now let's make an assumption here. Let's say that, I don't know, the side length of the diagonal, the side length of the pentagon and the diagonal of the pentagon are commensurate. Because why wouldn't they be? The gods don't say incommensurability is a thing. So then D and S must be commensurate. So if that's the case, we can perform Euclidean subtraction on it. I plunked our two equations up here. Let's remember them. So we start with D minus S. And, well, from equation 1, we can get D minus S, D1 minus S1 gives us D2. And then our next two smalls will be S1 and D2. S1 minus D2 gives us S2. That's from equation 2. But now we're back where we started because we have D2 and S2 are those two smalls. Well, that's going to give us D3. And then S2 minus D3 is going to give us S3. Both from equation 1 and 2 again. So what I'm trying to say here is we're stuck in an infinite loop where we are repeatedly doing equation 1, equation 2, equation 1, equation 2, equation 1, equation 2. And more importantly, we don't reach 0. So what went wrong? Why can't we do this? Well, because we assumed that the diagonal and side length of a pentagon are commensurable when they are in fact not. D over S is irrational. In fact, it is mathematically speaking the most irrational number because it's the hardest to calculate. That there's the example of where Hippasus proved. It appears several other times throughout the pentagon. It's in this Fibonacci curve. That's the mathematical representation of it. That's the infinite series you would use to calculate it by hand. It's a goated irrational number. It's awesome, maybe behind pi and d. It's found in nature. It's found in honeybee family trees. It's found in like how sunflowers arrange their seeds. It's found in spiral patterns and leaves. It's found in the galaxies. And it's an irrational number, meaning incommensurability is a thing. Uh-oh.
Tony, you don't think, shut up, God forbid, God forbid. Don't talk like that.
Uh-oh. The Akusmatiki were not thrilled with Hippasus's discovery. And while, as I said, very little is written about Hippasus himself, we don't get many people outwardly saying Hippasus got killed for this. But, I mean, it's all there, right? We've got he who disclosed irrational numbers and spread it among the common folks perished by drowning. We got the man who was revealed incommensurability. Pythagoreans hated him and said he was treated him as dead. Some say the gods punished the man who discovered this. And others say that same story for the one who delivered the method of inscribing a sphere in the dodecahedron, which, as we established in an earlier slide, Hippasus was very much doing. So, in how we in the industry say, Hippasus, yeah, he got whacked. He is. And that's the story of Hippasus. Thank you for listening. Hope you learned something. Any questions?
Do you want to use these papers?
Any questions?
Are these so important?
No, I'm done.
That
I'll gather
was
this
awesome.
Yes?
How did the science of bluegrass music help?
That was just a random video I saw a long time ago where this like hillbilly guy is like, he created 12 notes of music, Pythagoras did. And he did, I forgot, I didn't mention that because I've got a lot to cover. Goodness gracious. That's what I had there. This guy. He was talking about the music. And Pythagoras did the 12-note scale that we do with the pitches and harmonies. That's Pythagoras, yeah. Any other questions?
Do we learn the author now?
Yeah.
We're the author, yeah, sure.
8 minutes.
8 minutes of what? There. I didn't write much. Am I a math major? I'm a math minor.
What's your major?
Mechanical. Did anybody get the QR code?
No.
You skipped it.
I didn't have time. Okay, I'm sorry. I wanted to make sure that I was able to. Okay.
Very important.
Hell yeah.
Thank you.
I love being able to roll. I love being